What happens to stars after they die? Some explode, some shrink, and some, well, vanish into nothingness. Let's dive into 15 questions that explore the bizarre and brilliant afterlives of stars. These questions will help you in cracking various space and astronomy Olympiads. Ready? The term Schwarzschild radius usually describes properties of A. Red dwarfs, B. Pulsars, C. Black holes, D. Galaxies. The correct answer is black holes. The Schwarzschild radius defines the size of the event horizon, the boundary where the escape velocity equals the speed of light. It's the mathematical point of no return, calculated using general relativity. Now that we've started with black holes, here's another one. What type of radiation causes a black hole to evaporate over time? A. Schwarzschild radiation, B. Planck radiation, C. Kolmogorov radiation, D. Hawking radiation. If you went with Hawking radiation, give yourself a cosmic high five. This groundbreaking idea by Stephen Hawking reveals that black holes can lose mass via quantum effects near their event horizon. Over immense timescales, this could lead to complete evaporation. It's one of the most fascinating intersections of quantum theory and gravity. Now let's talk about our own sun. What's going to happen to it one day? What is expected to happen at the end of the sun's lifetime? A. Become a white dwarf, B. Become a brown dwarf, C. Explode as a supernova, D. Become a neutron star or black hole. The right trajectory for our sun is to become a white dwarf. As a medium-sized star, the sun won't explode. Instead, after expanding into a red giant, it will shed its outer layers and leave behind a dense, Earth-sized core that slowly cools, a white dwarf. Now let's move from gentle endings to one of the densest, wildest objects in the cosmos. When a neutron star rotates, it becomes A. Neutron dwarf, B. Rotor, C. Quasar, D. Pulsar. The answer here is pulsar. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation. As they spin, these beams sweep across space, and if aligned with Earth, we detect them as highly regular pulses. Let's stay on pulsars for a moment and check the next question. What kind of radiation do pulsars emit? A. Compton radiation, B. Lyot radiation, C. Planck radiation, D. Synchrotron radiation. If you picked synchrotron radiation, you're spinning in the right direction. Charged particles spiraling through intense magnetic fields generate this high-energy radiation. It's a signature feature of pulsars and helps astronomers study their composition and behavior. But have you thought how we detect them? Let's check in next question. What instrument is commonly used to observe and study pulsars? A. Laser interferometer, B. Radio telescopes, C. Magnetic spectrometer, D. Radar telescopes. Radio telescopes are our ears to the universe, and perfect for hearing pulsars. Pulsars emit strong radio waves, and large radio dishes like the Arecibo Observatory before it collapsed, or FAST in China, are specially designed to pick up these faint signals from distant pulsating neutron stars. Let's switch gears to another fascinating remnant. Which type of star is only stable due to the pressure of an electron gas? A. Neutron stars, B. Supergiant stars, C. White dwarfs, D. Blue dwarfs. The physics holding it together? That would be electron degeneracy pressure, and that's what stabilizes white dwarfs. This quantum mechanical force arises when electrons are packed so tightly that further compression is resisted, allowing white dwarfs to resist collapse even without ongoing fusion. Let's move on. Can you guess the answer for this question? Which one of the following objects is called a black dwarf in astronomy? A. A star that will become a black hole. B. A cooled white dwarf. C. A low radiation emitting star. D. A high radiation absorbing star. The right answer is cooled white dwarf. A black dwarf is a theoretical remnant, a white dwarf that has radiated all its heat and gone cold. But no black dwarfs exist yet. The universe simply hasn't aged long enough for one to form. Ready for something dramatic? What could cause a neutron star to collapse into a black hole? A. Increase in rotation speed. B. Loss of magnetic field. C. Mass exceeding the Tolman-Oppenheimer-Volkoff limit. D. Accumulation of dark matter. The correct trigger is when the neutron star's mass exceeds a specific limit, called the Tolman-Oppenheimer-Volkoff limit. Above this critical threshold, around 2 to 3 solar masses, the neutron degeneracy pressure fails. Gravity takes over, and the neutron star collapses into a black hole, forming one of the most extreme objects in the universe. Which brings us to our next cosmic threshold, the Chandrasekhar limit. What is the Chandrasekhar limit approximately equal to? A. 1.0 solar mass. B. 1.4 solar masses. C. 2.5 solar masses. D. 3.2 solar masses. The correct limit is around 1.4 solar masses. This is the maximum mass a white dwarf can have while still being supported by electron degeneracy pressure. If a white dwarf exceeds this threshold, either by accreting matter or merging with another white dwarf, it undergoes catastrophic collapse, potentially forming a neutron star or igniting as a Type Ia supernova. How are you doing so far? If you've gotten 7 or more right, you're officially a cosmic thinker. But there's more ahead. According to general relativity, what happens to time near a black hole? A. Speeds up. B. Stops completely. C. Runs slower. D. Repeats. Tick, tock, or maybe not. Near a black hole, time runs slower. This phenomenon is called gravitational time dilation. According to Einstein's general relativity, time passes more slowly in stronger gravitational fields. Near a black hole, time for a distant observer appears to nearly stop for anything approaching the event horizon. If you hovered near a black hole, you'd barely age at all. Let's get specific. Just how compact is compact? What is the approximate diameter of a neutron star? A. 1,000 kilometers. B. 10 kilometers. C. 100,000 kilometers. D. 10 million kilometers. A neutron star has a diameter of roughly 10 kilometers. Despite being several times more massive than the Sun, a neutron star compresses that mass into a sphere only about 10 kilometers across. 1 teaspoon of neutron star matter would weigh billions of tons. What element primarily makes up an average white dwarf's core? A. Carbon and oxygen. B. Helium. C. Iron. D. Hydrogen. The answer is carbon and oxygen, a dense, crystalline heart of a star. After helium fusion stops in low-mass stars, what's left behind is a carbon-oxygen core. That core cools and becomes a white dwarf, slowly radiating away its remaining heat. Next question. What distinguishes a Kerr black hole from a Schwarzschild black hole? A. It's made of dark matter. B. It rotates. C. It emits light. D. It exists only in theory. Kerr black holes rotate, and that changes everything. Unlike Schwarzschild black holes, which are non-rotating and spherically symmetric, Kerr black holes spin, creating a twisted region called the ergosphere. It might even allow for energy extraction via the Penrose process. Feeling the gravity of these facts? Let us wrap up with this final question. Which type of supernova typically leads to the formation of neutron stars? A. Type 1. B. Type 1a. C. Type 2. D. type I'm B. Type 2 is the dramatic finale you're looking for. These occur when massive stars run out of nuclear fuel and collapse. The core contracts into a dense neutron star, while the outer layers explode outward in a brilliant light show. So, how many did you get right? Let us know in comment section. If this sparked your curiosity, imagine what else the universe is hiding. Subscribe to Astro Academia for more deep space Olympiad preparations, narrated science explainers, and cutting-edge astrophysics content.